the last week of class. And it just sounds so nice. I enjoyed it too. So 3 more class periods today. I mean, we are going to start talking a little bit about applications today, but we're not going to have a ton of time for that. Maybe just a little introduction. We are finishing up sort of the more general stuff. Wednesday is our big application-focused day. I guess we'll start a little bit with that today. Hopefully if we have time. And then Friday we will review for the test. Test next Tuesday, is that right? Tuesday at 2:45 in this room. Okay. We are doing stuff that you might call beginning graduate level math here in metric spaces here. It sort of preps you for taking a class, a graduate level class out of this book in particular. This is Rudin. You might want to zoom in on that. It's a little hard to see with the gold trim. It says real and complex analysis. By the way, our complex analysis is not going to be out of this book. This is the book that's super heavy duty, graduate level. Everybody talks about Rudin. Very much the structure is definition, theorem, proof, definition, theorem, proof, definition, theorem, proof, with hardly any commentary, which makes it very difficult to learn from. Though there's also very hard problems in it too. Though after you're done with Rudin, once you've made it through the class, then you kind of look back and say, wow, that actually is kind of a neat book. It's structured so well, it's so beautiful, that kind of thing. Actually, my graduate level real analysis class actually was not out of this book, but my undergrad real analysis class after Bethel, which I did take another undergrad real analysis class, was out of this book, which is called Baby Rudin. This is also by Walter Rudin. It's called Principles of Mathematical Analysis, and everybody calls it Baby Rudin. Okay? Baby Rudin is 19th century math, okay, which does include metric spaces. But Rudin, that's 20th and 21st century math. Actually, this was printed in the 20th century here, this particular copy. So I'm sure this is just 20th century math. Okay? Does this abstract stuff have benefit for you? Okay? Well, if you take topics in the spring, and I know not all of you are doing that, it will definitely have benefit for you. Okay? We do in topics in math, which we're doing complex analysis, we do some topology in there. Talk about open sets for the most part. We keep it at a minimum. It's not a real big deal in there, but it does give you a leg up on the students who haven't had this class who are going to be in topics. So maybe you'll be helping them with the basic topology stuff in that class. Metrics and norms still come up in that class.
Like Christmas norms?
Christmas gnomes? Christmas norms, I said. Norms, okay. Metrics and norms. If you're not taking topics and you're saying, oh, you know, this, I'm not going to do that, that's not going to benefit me, well, maybe you're going to be a student teacher, maybe you're going to be a teacher. And it's still, I think, a good thing to get more practice with abstract math and proofs because it does give you a bigger picture. And when you have a bigger picture of things, then you see how things fit together better, and that does make you a better teacher of including algebra, pre-calculus, calculus classes. That's a benefit to you. What if you're going to be in the business world? Well, it still can be a benefit. I was talking to Miranda about how people in business are pretty impressed even if you can do basic things with spreadsheets. Okay, I'm serious. Even if you can do pretty basic things with spreadsheets, quantitative stuff, that's impressive to people. So now you can deal with metric spaces. Spreadsheets should be no problem, okay, right? You know how to problem solve, you know how to think abstractly, you know how to put things together. So it can still be a benefit to you. I should also say that when I was in grad school, I was taking real analysis, both the extra undergrad class and a graduate level course, and there was a PhD student in accounting who was in there. I forgot his name. He was an acquaintance. I went golfing with him once, but I forgot his name. So if you ever watch this video, if you ever happen to stumble upon it, you know who you are. Contact me because I'd like to get in contact with you again because I forgot your name. But anyway, he was a PhD in accounting, and he was taking real analysis because he had to, okay? Doing a PhD in accounting. Actually, he said a PhD in accounting is not that much different from a PhD in economics, say, in advanced economics. They do a lot of mathematical modeling, which does include, for example, probability models, which really advanced probability models do need graduate level real analysis. Measure theory, Lebesgue integration, that kind of stuff is is in this book, and they actually do need that for their models. All right, let's get to content now. Let's first look at a new example. Well, I did mention this example last Friday. So our new space X that I did consider briefly last Friday is C of AB. Again, here's the way the book writes it. I usually don't bother with the parentheses, and I usually just write that. So if on the exam I happen to write that one, don't be confused by this. This is the space, the set, the collection of all continuous functions defined on the closed interval from A to B. We're going to say real valued functions. All real valued functions. They can have other outputs like complex numbers too. But I'm going to say all real valued functions defined and continuous on the entire interval from A to B. By the way, this is related to linear algebra too. This is a vector space, also called a linear space, what we call a vector space. The elements of this space are functions. The points are functions. Is it just a difference in terminology? We're just calling the functions points? Yeah, well, partially. We still know their functions. We can still make their graphs. And the points on the graph, by the way, are not the points I'm talking about. The functions themselves are the individual points of this space, the elements of this space. The norm that I talked about last time, which is in the book, it's got a bunch of different names. Usually a subscript of infinity is put here. Sometimes it's called the infinity norm. I'm mostly used to calling it the sup norm, because it's a supremum that's calculated by calculating the supremum of the absolute value of the outputs as the inputs range over the closed and bounded interval. Because our space consists of continuous functions defined in this closed and bounded interval, this sup is not infinity, right? We know by the extreme value theorem that this sup is going to be finite, and moreover, actually, it's going to be attained. There's going to be an input, at least one input that you can plug in here that's going to give you the sup. You can call it a max as well. If we were just talking about bounded functions, not necessarily continuous, then you'd have to use the sup, because the max might not be attained if the function was not continuous. We know that from the extreme value theorem and from examples we've considered before. I'm going to leave it as a sup. Sometimes it's called the uniform norm too, because here's a sort of application. Because uniform convergence of a sequence of functions on a closed interval like this is equivalent to convergence in the metric related to this norm. What is the metric related to this norm? By the way, anytime you do have a norm that measures the size of something in a space, its distance to the origin in that space, assuming it's a vector space, you're going to have a metric too. And you can always calculate the distance between points in that space once you have the norm by taking the norm of the difference between the points. You've got to be able to do a subtraction though, so it's got to be a vector space. This is a vector space. You can add and subtract. That's how you calculate the distance between two functions in this space. In terms of the sup, it would be this. And like I just said a minute ago, uniform convergence of a sequence of functions in this space is equivalent to convergence with respect to this metric. I didn't call it d sub infinity here, I could. D sub infinity. You could say it's a theorem. In fact, it's actually a theorem in our book, which I'll mention in a second. In the previous chapter, actually, back chapter 7. A sequence of functions, there's the chapter 7, converges uniformly to F on this closed interval from A to B if and only if the sequence of numbers v sub infinity fn comma f converges to 0. Actually, that's not how we defined convergence in a metric space, but it's going to be good enough to say this sequence of numbers converges to 0. Why is that? Well, v sub infinity of fn comma f is the sup of these values. And I hope this looks a little familiar. Go back to chapter 7 if you've got your book. Get it out. Go back to chapter 7. Look at page 249. One of the more important theorems in chapter 7 about uniform convergence of a sequence of numbers. This thing back in that section was called M sub n. Now, there were two theorems where M sub n was used. One was the Weierstrass M test, and one was this other theorem. And looking at theorem 7.4, page 249, you got a sequence fn that converges pointwise to some function f on an interval. And if you assume these mn's go to 0, that's equivalent to that sequence of functions converging uniformly to f on an interval. Those are the mn's from this theorem. It's related to this metric. So you could consider that to be an application of the abstract idea of a metric space here. It's not much of an application because it's not much of a translation from this theorem to this stuff. Again, we're going to do a more significant application. Start a little bit today, but mostly that's our topic for Wednesday, is to do a more significant application. I think it is probably worth showing, spending a little time thinking about why the triangle inequality works for this, which will then imply the triangle inequality works for that too. Anytime you know the triangle inequality works for the norm, it's going to pretty easily follow that it works for the metric. So why is the norm of the sum of two functions, actually, you can do it with the sum, less than or equal to the sum of their norms with respect to this particular norm is what we're talking about. Talking about this particular norm. Once you've got the triangle inequality true for the norms, let me just remark over here some equations and inequalities that verify that it's true for the metric too. So I guess I'm doing that first. So I'm considering proving the triangle inequality for the metric once I know it's true for the norm. So I'm going to assume the triangle inequality is true for the metric. The first step here is just a matter of trick. Adding 0 in a convenient way. The 0 function, which I'll call h. Well, actually, h is not the 0 function. H is an arbitrary function. But I am adding the 0 function in a convenient way, negative h plus h. Once you know the triangle inequality is true for the norm, you can apply it now after you've used that trick to say this. And that's the same as the sum of the distances between f and h and h and g. So once you know it's true for the norm, after you do a little trick here, with adding 0 in a convenient way, you can show it's true for the metric as well. But why is it true for the norm? That's the more significant issue. Well, by definition, this is the soup of these values as x ranges over the closed interval from A to B. Similar kind of thing for the norm of f itself, similar kind of thing for the norm of g of itself. Here's what it would be for the norm of f, back over here, can you see that? And for the norm of g, I just replaced the f with the g. Let's call this thing alpha and this thing beta, just to give them names. I could say why is this soup less than or equal to alpha plus beta? How would you show that is what I'm trying to get at. Well, this is a supremum of a set, this set, call this set A, say. To show that supremum is less than alpha plus beta, all I need to do is show alpha plus beta is an upper bound of this set. Since the soup is the least upper bound, good review here in chapter 1. That will imply this inequality is true. I'm not really writing out a full proof, but let's just think about it here. Use the triangle inequality for numbers from chapter 1 to say that for any x, for all x in the interval from A to B, the absolute value of f of x plus g of x is less than or equal to the absolute value of f of x plus the absolute value of g of x. That's the ordinary triangle inequality from chapter 1. Think of x as fixed. This is true for any x in the interval. F of x is a number, g of x is a number. The absolute value of f of x plus g of x, we know from the ordinary triangle inequality in chapter 1 is less than or equal to that. But hey, no matter what x is in the interval, this has got to be less than the soup of those values. And the corresponding thing, the absolute value of the g of x's, have to be less than the soup of those values. This is, for any x, less than or equal to alpha plus beta. It's true for all x. Therefore, alpha plus beta has to be bigger than or equal to the soup as well. It's bigger than or equal to all these values for all x in the interval. It's an upper bound of the set. Therefore, the soup of the set is also less than or equal to alpha plus beta. I could see putting that maybe as a proof on the final exam. I said it verbally. I hope you weren't tuning out. All right? It's actually not that hard. I mean, to be explicit about what you're trying to do, again, give this a name, call that alpha, call that beta. You want to show that the soup of this set is less than or equal to alpha plus beta, which means you need to show, because the soup is the least upper bound of the set, that alpha plus beta is bigger than or equal to all these values as x ranges over the interval. So give me an arbitrary x in there. By the ordinary triangle inequality, this is true, but by definition of alpha and beta, that's less than or equal to alpha, this is less than or equal to beta. Their sum is less than or equal to alpha plus beta, and that means alpha plus beta is an upper bound of the set. So this is bigger than the soup of the set. The soup is less than. Okay? In the big scheme of things, it's actually not that hard. So that's why that's true, which then implies this is true. By the way, this kind of argument here works no matter what your norm is. And no matter, anytime you're creating a metric using a norm, this exact same argument verifies the inequality for the metric when you know the inequality is true for the norm, the triangle inequality. Exact same argument. That's the benefit of the abstraction. One big benefit is it helps you prove a bunch of things all at once. The same general fact can be proved in the abstract setting, and you prove it once and for all. It also unifies what's the key reason why things work. It teases out exactly the key reasons why things work. Next example I want to consider is going to be a metric space that we're going to use on Wednesday in our application. Sometimes called capital sigma sub 2. What is this? This is a sequence space. The elements of this space are sequences. You've read about sequence spaces. You should have. Section 8.5, like the space of all bounded sequences, the space of all sequences that converge to 0. Those are all metric spaces that you read about in section 8.5. This is a new sequence space. The set of all sequences, xn, not a typo there, this is a collection of sequences. That's our notation for sequences. We're going to start n at 0 actually instead of 1. So let me put that little extra bit of notation there. In our application on Wednesday, we're going to start, that will even maybe start today, we're going to start at 0 instead of at 1. Because 0 is going to be our initial condition, x0, our seed. Where xn is either equal to 0 or 1 for all n. So the sequences in this space consist of, if you think of them intuitively as lists of numbers, just a bunch of zeros and ones. A binary space, maybe called that. You could, I suppose. A bunch of zeros and ones that go on forever. As a function, it's a function from the natural numbers to the two-element set 0, 1. These sequences are functions of this form. This turns out to be a metric space. And, well, what's the distance between any 2 points in this space? X is going to be the shorthand symbol for that. Y is going to be the shorthand symbol for this. I'm going to define a distance, which is not the only measure of distance that could be made. This is just a convenient measure of distance. By an infinite sum, going from 0 to infinity, the absolute value of xn minus yn divided by 2 to the n. It's an infinite sum. Does it converge? What do you think? The answer must be yes. If you had to give a reason why it converges, do you think you could give a reason? Prove this converges no matter what x and y are, no matter what sequences these are. Any idea? The fact that these are zeros and ones is relevant. For each n, this quantity is less than or equal to something simpler. 1 over 2 to the n. And we know the series that adds up 1 over 2 to the n, it converges because it's geometric with common ratio less, having an absolute value less than 1. Common ratio is 1/2. This converges to, in fact, 1 over 1 minus 1/2. It converges to 2. Therefore, by the comparison test, this series converges no matter what x and y is. And hey, it's going to always converge to something less than or equal to 2, no matter what x and y are. Interesting. The distance between points in this space is never bigger than 2, according to this metric. Can that be imagined? Well, sort of. I mean, you can imagine spaces as blobs and the individual points in the space being points. These points are abstract points, but in reality they're sequences distances that we measure, we can imagine like this if we want, but realize in doing that imagining, it is just your imagination. It's, I don't know what to call it. How real is that? It's as real as the picture, essentially. And the picture can still help you understand things better, help you understand more abstract theorems, but the picture is not the proof. You need the properties, the arithmetic, algebraic type properties of metrics, for example, to be able to prove things. In fact, one thing we're going to prove on Wednesday is that a certain function, a certain map, from this space to itself is continuous, where this map is a very special map called the shift map. In math, in case this wasn't clear, anytime you say map, it means function. Though typically when you say map, you're kind of emphasizing it, that you're imagining it geometrically. That's doing the mapping of points in one space to points in another, so it's sort of got a geometric connotation. The shift map, typically called little sigma, from the space to itself takes a sequence in this space, which I'm going to go ahead in the formula for this function, I'm going to go ahead and write out as an infinite list. Though I won't bother putting commas between the zeros and ones. x0, x1, x2, x3, x4, etc. There is your arbitrary sequence in the space. These x's are zeros and ones. They don't represent a number, by the way. I mean, you could make them represent a number if you wanted to, but the elements of the sequence are just, elements of the space are sequences of just symbols, the zeros and ones. You don't even have to give numerical values to them except when you think about the metric itself. What this function does is it shifts the sequence. It shifts everything one unit to the right, to the left, excuse me, deleting the first entry. So you get a new sequence whose first entry is x1, x2, then x2, then x3, then x4, etc. x0 has been deleted. You've shifted everything to the left. It's going to turn out that sigma is continuous with respect to this metric space and that metric. Continuous in the definition of continuity from last week. You can define it in terms of epsilons and deltas. You can also define it in terms of pre-images of open sets. The open sets themselves have to be defined in terms of open balls, which still involve the metric. I'm talking pretty high level here. When you've worked with this stuff enough, maybe you're feeling pretty confused. When you've worked with this stuff enough, the things I just said in the past 30 seconds, like, make intuitive sense, okay? But you gotta work with it a lot. You gotta learn how to think abstractly in this context. We'll prove this on Wednesday. Today I'm just stating it. And the fact that it's continuous will be important for our application. Okay. With our remaining time, I think perhaps the best thing to do would be to, well, besides introducing the application in the last 5 minutes or so, would be to emphasize some other real important facts about topology and metric spaces. Just to, again, I'm trying to emphasize what I consider to be the most important things, whereas there's a lot of other content examples, for example, in the book that you should read about to help you get a deeper understanding. In class, with the time that we have, I'm trying to emphasize the most important things. The theorem I'm going to write down is of fundamental importance here. I have mentioned the theorem before, mostly just verbally. I didn't write it down, I don't think. If I did write it down, I might have just written it down in on the real line or an R2 or something. We were talking about Euclidean space. But this is true in abstract metric spaces, and it's even true in more general settings. There are more general settings than metric spaces. Just pure topological spaces that don't necessarily have a metric, don't necessarily have a notion of existence. How in the world is that subject done? Pure topological spaces, pure set theoretic point set topology, is described completely in terms of just open sets. I don't know that I want to say any more than that, because it might just confuse things. But if you just think in terms of points in the space and defining what it means to be an open set in kind of a real abstract sense to satisfy certain properties, you can do everything that we've done, for example, even with compactness, in those pure topological spaces. And the theorem I'm about to write down is true in that setting as well, although in the abstract setting it's more of a definition instead of a theorem. So we're given a metric space X comma D. So X is the space, D is the metric. They go together. We call it a metric space. A set O in X is open in X if and only if its complement, its set complement, is closed in X. There are plenty of sets. First of all, don't misunderstand this. This does not mean every set is either open or closed. There are plenty of sets that are neither open nor closed. So it's not they're not complementary ideas in terms of the collection of all possible sets. It's not an either-or thing. Either a set is open or it's closed. There are plenty of sets that are neither open nor closed. And in fact, there are two sets in any space that are always both open and closed. The empty set and the entire space are always both open and closed. What it's saying is, you got an open set, its complement, set complement in that space, it's got to be closed. If this is O, drawing dashed lines to emphasize it's open, although you don't have to draw dashed lines. Its complement is everything outside of that, including, in the picture, the boundary of O is outside of O. Everything outside of O, which includes the boundary of O in this picture, in this intuitive picture, would be the set complement of O in X. And in the picture, I hope intuitively that makes sense, that that would be closed. That's not a proof, though. This is a fundamental fact to know. Let's outline its proof. Could the proof of this, maybe one direction, be on the final exam? I think so. At least one of the directions is a little easier than the other direction. This direction, from right to left, is a little easier. If you assume the set complement is closed, show the set itself is open. It's a little easier to prove, I think. What do you have to do? To show something's an open set, you've got to show that every point of the set is an interior point of the set, right? I hope that's something you can spout out within a few seconds. A few seconds of thought. A set is open if and only if every point in the set is an interior point of the set. That should almost be second nature. So I gotta say, give me a point in the set. I gotta show it's an interior point in the set. I gotta find an open ball centered at that point that's entirely inside the set. Because That's what it means to be an interior pointing set. I must have to use this fact. I'm assuming that set is closed. How am I going to use that? To be closed means what? It means it contains all its limit points. X is an O. That implies X is not in the set difference X minus O. It's not in the complement of O. Which means it can't be a limit point of X minus O. Because if it were a limit point, it'd have to be in X minus O. Because X minus O is closed. Get that? It's in O, so it can't be in the complement of O, which means it can't be a limited point of the complement of O, because if it were a limit point, it'd have to be in X minus O, because X minus O is closed. X is not a limit point of the complement of O, since that complement is closed. What does it mean to be a limit point? It means give me any positive radius R. The open ball centered at the point contains a point of the set other than X. So it's not a limit point. There must be some open ball that doesn't contain any other point of the set. Get that? If X were a limit point, then any open ball around X, no matter how small, would contain a point of this other than X. Oh, X is not in there. Since it's not a limit point, there must be some open ball, some positive radius, so that the open ball centered at X does not contain any other point of the set. Maybe I should state this in terms of deleted neighborhoods. There exists a positive R such that the deleted neighborhood, the open ball centered at X of radius R, take away X itself, the deleted neighborhood of X, intersect with this set, X minus O, the complement of O, must be the empty set. What was our goal? Our goal was to show X being an O is also an interior point of O. Our goal was to find an open ball centered at X entirely inside O. This basically does it. This does imply that the open ball of this radius R centered at X is a subset of O, and that finishes that direction of the proof. Maybe a picture helps you understand this. The picture's not a proof, but a picture helps you understand that last implication. Come back over here. X is in O, not in the complement, which is a closed set. There must be some R centered at X that, if you take out the middle point, it doesn't intersect X minus O. Even if you included the middle point, it would not intersect that, but in terms of the definition of what it means to not be a limit point, it's probably best to say it in the way that I did in terms of a deleted neighborhood. And that is going to mean this set, including the center, is a subset of O. So the picture helps you believe it and helps you figure out the argument, but the argument itself is pure logic. What about the other direction? I think that's a little trickier. I mean, I'm not saying this was easy. I mean, anything abstract typically is a struggle. especially when it's got more than 1 or 2 steps, and this I guess has 4 steps. But it is straightforward when you thought about this stuff enough and you work through the definitions and think about them carefully. The other direction I think is a little trickier, mostly because I think perhaps the best strategy for the forward direction is to actually prove the contrapositive of the forward direction. I think is the best strategy, and that's probably the trickiest thing, is to realize that that's the best strategy. At least I thought it was the best strategy. In other words, to prove that O being open implies the complement of O is closed, I could assume the complement of O is not closed and show the O itself is not open. By the way, the complement of O being not closed doesn't mean it's open, right? Because there are sets that are neither open nor closed. And that's the second tricky aspect. Assume the complement of O is not closed. I want to show O itself is not open. Meaning, think about this, to be open means there must be some open ball centered at X, an arbitrary point of O, that's entirely inside O. So to show O is not open, I need to find some X, so that for all open balls centered at that X, it's not entirely inside O, no matter how small that open ball is. Using the fact that this complement is not closed. Closed means it contains all its limit points. So not closed must mean there's a limit point that's not in the set. To be closed means a set contains all its limit points. So if it's not closed, there must be some limit point that's not in the set. Exists a limit point, little x, of this complement such that little x is not in the complement. That's what it means to not be closed. Because closed means it contains all its limit points. It is still a limit point of the complement of O. So for any radius of an open ball centered at X, there must be points of the complement in that ball that are not equal to X. And that's going to mean that X is not an interior point of O. X is not a limit point of this, and it will also not be an interior point of O, so O can't be open. Because open means it's got to contain all its interior points. How should we say that here? It is a limit point. Say it like this. Since X is a limit point, of the complement of O for all positive R, the deleted neighborhood centered at X of radius R intersect with the complement of O is non-empty. Which means, so for all positive R, the open ball of radius R centered at X is not a subset of O. Again, the picture can help. X is a limit point of the complement of O. Maybe pretend it's a boundary point here. Pretend it's not in the complement of O though, so maybe pretend there's a little dash bit here. So it's on the boundary of O, which is the same as the boundary of the complement of O. But pretend that the complement's not closed, so pretend it's a limit point but not in the set. No matter how small R is, that open ball centered at that point will contain points of the complement other than X. And you can see in the picture that that means it's not a subset of O. It contains points in the complement of O. It can't be a subset of O. Once you see the trick of realizing and proving the contrapositive, perhaps this is the same level of difficulty as the other one, but I think again it's just realizing the contrapositive is perhaps the best way to go. That makes it tricky. I was trying to prove it without doing the contrapositive and I was getting stuck. Okay, so this is a fundamental fact to know. It's a theorem in metric spaces. It really is a definition in abstract topology. You define what open sets are to satisfy certain properties, and then you define closed sets to be complements of open sets. That's the approach in a more axiomatic approach to topology without talking about metrics. And actually, the theorem about continuity of F is continuous if and only if all the preimages of open sets are open, that becomes a definition in the abstract topology as well, defining what it means for a function between two abstract topological spaces to be continuous. It's not a theorem to prove, it's a definition. I hope you've experienced that enough that you know in axiomatic math, oftentimes what was a theorem in one context becomes a definition in another context. I was thinking there was one more important fact I wanted to mention before I introduce our application. But now I'm forgetting what it was. Oh. I want to re-emphasize in the abstract setting, metric spaces, any union of any collection of open sets is open. If these are open, then the union is open in any metric space. And that can be proved with a proof similar to the way I did that with the real line. Do you remember the first day we did topology, which was before Thanksgiving? We were talking about topology of the real line, and I proved that I believe it was that first day, the union of an arbitrary collection of open intervals was open, an open set. We did that day before Thanksgiving. That would have been, what, lecture 31, I think? Also, if you've got a finite collection of open sets, their intersection is open.
These are just statements you're walking through.
Yeah, I'm writing down some properties of open sets in metric spaces that can be proved in metric spaces. You got a collection of open sets in a metric space. Any collection. The omega here can be any set. Could be an uncountable set. This could be a union of uncountably many sets. It's an open set. An intersection of a finite number of open sets in a metric space is open. I'm not really writing down full theorem statements here. I'm verbally describing them. It also turns out the entire metric space and the empty set are open, like I mentioned. The empty set by, what's the word? Vacuously open. It contains all its interior points because it doesn't have any any points. Every point of the empty set is an interior point of the empty set because the empty set doesn't have any points. Question?
Is that an arrow
Where?
from open to what?
That's a 2 there.
It's just saying O is open.
What?
Yeah, this is an arrow, sorry.
Okay. Oh, gotcha.
These are open. It's pretty trivial to prove the entire space is open as well. Give me any x in the space. Any open ball centered at x is going to be a subset of the space by definition. These become definitions at real abstract topology instead of theorems. Definition of what it means to be open is you've got this collection of things that you call open sets. They have to satisfy these properties to start with in the axiomatic approach. One other thing I did want to mention, and I think I'll talk about this a little bit more on Wednesday, is in section 8.3 you had definition of what it means to be open in some sets. That's not the whole space. You got the whole space. Say X is R2, the plane here. So this drawing is in the plane, and you've got some subset of the space. Call it capital A. What does it mean for a set to be open in A? I even mentioned this in class. There was a big emphasis in the reading of section 8.3. A set O that's a subset of A is open in A if there's some bigger open set, say, in R2 or X. Call that bigger open set, I don't know, U, such that O is the intersection of A and U. And this applies even if A here in this picture is a closed set containing all its boundary points here, so that O contains these boundary points as well. O is not open in X in this picture, but it is open in A, because there is some bigger open set in X so that this intersection equality is true. So we read about that. Had a few completion problems about that. I think I will talk about that a little bit more on Wednesday. And we'll also start to talk about what to expect for the final exam on Wednesday. We'll start our review on Wednesday and we'll finish it on Friday. To end class today, I just want to briefly, just in a few minutes, show you something that I showed you before. Here's our application. It's going to be Wednesday's main focus. Application of metric space ideas, topological ideas, to studying the behavior of the logistic mappings f sub mu of x equals mu x times 1 minus x when mu is positive, especially when mu is 5, on something called its invariant Cantor set. We're going to apply the ideas, especially the space of sequences of zeros and ones and its metric in that shift map. Are going to be applied here. I'm not going to be able to prove too much, I think. I'm perhaps only going to have time to highlight the factual things and illustrate them with Mathematica, but maybe we'll have time to prove 1 or 2 things. I showed you this before. Back when we were talking about sequences, chapter 2, you can define a sequence by a recursive equation. And in Mathematica, nest list is the best thing to use to see the iterates, the elements of the sequence. If you start with a seed, x0 is 0.1, and you use this function 4x minus 4x squared, which is part of this family, by the way, when mu is 4. Here are the first 100 iterates, which are the first 101 elements of the sequence. Well, this one gets pretty close to 0, but not equal to 0. And we've described this before as being kind of chaotic. The points bounce around the number line and kind of fill it in densely. Give me any point between 0 and 1, there's going to be some element of the sequence that's within any epsilon of that point. The set of all subsequential limits of this, when we talked about lim sups and lim inps, is the entire closed interval from 0 to 1. This fills it in densely. Also make a graph like this to see the erratic behavior. It's not random. It's not a probabilistic thing. There are patterns to this. One pattern is anytime the iterate is close to 1, the next one is close to 0. Another thing to notice is anytime your iterates are close to 0, they get bigger, and if they're real close to 0, not by much. But then when they get close to 0.2, then they start increasing pretty rapidly. The behavior is most chaotic without much pattern when the values are between about 0.5 and 0.8 or so. It's hard to predict what the next value will be. And we also looked at the cobweb plots of those things. Oh, I can type that here. I made a manipulate with this before, but I guess I'm not doing that right now. This produces one of those plots. It started at 0.1. X0 was 0.1. Plug that into the function, go up to the red graph. X1 was I think 0.36. Then you go to the blue line, which is the line y equals x, and you go up or down to the red graph, and you continue that pattern. And basically, in the case where mu is 4, you get this very dense picture that we did animate in the past, showing that it's very chaotic and in some ways random, but it is deterministic. You can make a frequency histogram for the values, and you can think of this probabilistically if you sort of didn't know what the previous value was. Your best bet, probabilistically, is that the value you're about to look at is either close to 0 or close to 1. So it can be thought of somewhat probabilistically, but it is a deterministic system. We want to understand what goes on. When mu is 4, you get this kind of picture. When mu is 5, however, or in fact, even anything just barely bigger than 4, this picture is still true. However, we'll see what happens on Wednesday is that most points still escape. They escape the interval. The graph goes above 1. And if the graph goes above 1, for example, at 0.5, when you plug 0.5 into the function, the output will be above 1. And then the next output will be negative, and then go off to minus infinity, actually, if you continue the diagram in the bigger window. So once mu gets above 4, you still have chaotic behavior, but on a much smaller set of values. So it's still, in some ways, a big set. And the symbol space, sequences of zeros and ones, will help us understand what's going on. That's the idea. See you on Wednesday.